Spirit of Math, the channel devoted to mathematical curiosities. In today's video, I will guide you through three proofs of the infinitude of prime numbers, namely Euclid proof, which is the most simple one and the oldest one. And then we will dive to Fermat's proof, which at the beginning was false and has been fixed later. And the core of this video is the Fürstenberg proof of the infinitude of prime using a curious topology on the set of integers. So let's start. A prime number is a natural number greater than 1 that has no divisor other than 1 and itself. And for instance, the first prime numbers are 2, 3, 5, 7, 11. And the prime numbers are the building block of natural numbers. Namely, we have this result for any integer n bigger than 1. It can be decomposed to a product of prime numbers at some powers. So n can be write p1 power alpha 1, p2 alpha 2, where pe are prime and alpha e integer. So any integer has a prime as a divisor, for instance. For instance, 60 is equal to 2 power 2 times 3 times 5. Now, there are hundreds proof or more of infinitude of prime numbers. And for instance, the oldest one is Euclid's proof in 300 BC. Euler gave a proof in 1737 using the harmonic series. Then Legendre and Dirichlet also gave a proof based on number theory, and Pierre Fermat in 1640 gave a proof which at first was false and has been fixed later. And Paul Erdos actually gave many sample proofs of the infinitude of primes. And recently, Fürstenberg gave a proof which is quite curious because it uses a topology on the set of integers. And we will, in this video, we will review the Euclid's proof, Pierre de Fermat proofs, and the core of this video is Fürstenberg proof, which we will explain it in detail, and we will define what topology means, because it's an advanced topic in mathematics. So let's start. We denote by capital P the set of prime numbers. Euclid's proof, it's so easy, it's by contradiction. So we suppose that the set of prime number is finite, equal to p1 times pr. And we consider this natural number p1 times p2 times pr plus 1. And since we have seen that any integers has a divisor, a prime divisor, so there will exist pi which divides n. But P1 is also in this product, so it will divide this product. So it will divide 1, which is impossible because Pi is a prime number. And we get that the contradiction. So it's the Euclid's proof, which is so easy. Now we will tackle Pierre de Fermat proof. Fermat consider this sequence of natural number known as Fermat's numbers, and he claimed that these numbers are prime. So since there are infinite number of such Fn, he deduced that the set of prime number is infinite. But unfortunately, these numbers are not prime, and the first one is F5. F5 is equal to this number. It's not prime because it has divisors this prime number as this one. So Fermat's proof actually was false, and it has been fixed later by using this number. So the first property is that the product of the n-1 Fermat numbers is equal to the n1 Fn-2. So we have this identity. This identity is easy to show. It can be done by induction. So for n equal to 1, we have F0 equal 3, and F1 equal 5, and 3 is equal 5 minus 2. So this formula is true for n equal to 1. And we suppose that this formula is true for n, and we will show it for n plus 1. So for L plus 1, we get that this product is equal to this one by Fn, but by induction hypothesis, this is equal to Fn minus 2. So we got, now we replace by the expression of Fn, and we get this formula which gives us what we want to prove. And so we have this identity. Based on this identity, we can show that actually Fermat's numbers are coprime. If we take m less than n, then the two Fermat number Fm and Fn are coprime. This means that the only common divisor of these two numbers is 1. So we will prove that by using our formula. So let D be a common divisor of Fm and Fn. Then D will divide this product, because in this product we have Fn, since Fm is less than equal. Donc this D divides this product, so it will divide Fn minus 2, but it divides Fn, so it will divide 2. So D has two possibilities, D equal to 1 or D equal to 2. D cannot be equal to 2 because Fermat's numbers are odd. So we get that D is equal to 1. Now with this property we can prove that prime numbers are infinite. So let's we consider this map from the set of Fermat's number to the set of prime numbers, and to any Fermat's number we associate the smallest prime divisor of Fn. Okay, now since we have seen that Fermat's number are coprime, this map is injective. So we inject an infinite set into the set of prime numbers, so we get that the set of prime number is infinite, and we have down. So it's the Fermat proof, or actually the fixed Fermat proof. Now let's tackle Fürstenberg proof. First, Fürstenberg was an American Israeli mathematician born in Berlin, and he immigrated to the United States. He studied at Yeshiva University and received his PhD from Princeton University in 1961. He is famous for many results in mathematics, and the most famous one is his topological proof of the infinitude of prime in 1955. And he received many awards, Israeli Prize in Mathematics and the famous Abel Prize in 1990, and unfortunately he died in the same year. So let's go through the Fürstenberg's proof. We need to define what is a topology on a set X. So a topology on a set X is a collection of sets F equal to OI, where I ran through an index set. This OI are called open set, and this collection of open set satisfies some properties. The first one is that the empty set and X itself are open, and if you take any union of opens, you get an open set, and any finite intersection of open is also an open set. So this is the definition of a topology. And a set is closed if its complementary is open. Okay, so now we now know what is a topology. The most important example are the canonical topology of Rn. Indeed, in Rn we have a distance, the Euclidean distance, and with the Euclidean distance we can define balls of radius r. A ball of radius r are the set of vector in Rn which are at a distance less than r from X. And with that we can define what is an open set. An open set is a subset of Rn is open if for any X there exists R strictly positive, such that the ball of radius of center X radius R is in O. So it is the canonical topology of Rn. And now we define the topology on Z given by Fürstenberg. It's a curious topology. So first, Fürstenberg introduced the equivalent of ball. So he take A, B in Z with B positive, and he define NAB equal to the set of A plus NB, where N run through Z. This is the equivalent of ball in Z, and he define an open set of Z is either empty. Suppose that the empty set is open, and for any A in O there exists B positive such that NAB is contained in O. So you see that it's like the definition of the topology on Rn. Just we replace the balls by this NAB sets. So we have now the definition of open. So now we will show that actually this defines a topology on Z. So we start by remarking that the empty set and Z are opens, and we consider a family of open set for this with this definition, and we will show that their union is also an open set. So we take an element in this union A. So we know that this means that A is in some open OI naught, and since OI naught is open, there exists B positive such that NAB is contained in OI naught, and we have shown the property of open set. So this family is actually an open set. And now we will do the same for the intersection. We consider a finite family of open sets, and for any A in this intersection, we take A in this intersection. This means that for any A is contained in OI, and this means that there exists BI positive such that NABI is contained in OI. And now we use this property. NAB1 B2 is contained in NAB1 intersection with NAB2. It's easy, since if you take one element here, it has the form A plus NB1 B2, but it's also can be A plus NB something B2 or something B1. So we get this inclusion. Now we use this inclusion to show that NAB1 B1 is contained and all the intersection, and this is contained in the intersection of OI, and we have down. So now we get a topology on Z. So far we have shown that Z is a topological space, and the non-empty sets are infinite because they contain these balls which are infinite. And now we have the key properties we which will permit us to show the infinitude of prime numbers. The first one is that NEB is an open set. This is easy. If you take A plus B and NIB, you can see easily that NA plus NB is contained in NB, because any element here can be written A plus NB plus NB, A plus N plus NB, and it's contained, so it's easy. The most difficult part is this one. We have this NAB is equal to the Z minus this union of NI plus IB for I between 1 and B minus 1. So if we establish this relation, since this union is closed, we deduce that NAB is closed. So if we show this equality, we will deduce that NAB is closed. This means that NAB is at the same time open and closed. So let's show this equality, and in my opinion is the core of the proof. It's the most difficult part of the proof of Fürstenberg's proof. So let's show this equality first. So we need to show that this is contained in this set is contained this one, and conversely this set is contained in this one. So we take first an element here, we will show that it's here, and conversely. So let's go. So we take Z equal A plus NB and NIB, and we will show that it is in this set. So we will show that it cannot be in any of this NA plus EB. So we will suppose that it's the case. We suppose that Z is in one of this NA plus AB. So there exists I between 1 and B minus 1, such that Z is equal A plus A plus N. This means that it is in this. So by comparing these two relations, we deduce that A is equal NB minus NB, which means that A is equal N minus NB. This means that B divide E, but E is less or equal to B minus 1, which is impossible. So Z is equal is in this set, and we have this. The converse is a little bit tricky. So if we take Z in this set, we will show that Z is actually in NAB. So first we perform the Euclidean division of Z by B and of A by B. So Z is equal NB plus R, where R is less than B, and the same here. And we write Z as A plus minus MB plus S, which is equal to 0, minus B minus S minus B minus B minus S is actually A, and we get A minus E plus E is equal to 0. So this we have this relation, and we also perform the Euclidean division of R minus S by B. and we get this relation. If we replace here, we have Z actually is in NA plus EB, but we know that Z cannot be in NA plus EB, so the only possibility is that I is equal to 0. And we get I equal to 0 and Z is in NAB. And we have shown this property. So so far we have shown that Z is a topological space, and any non-empty set is infinite, and NAB are open and closed. This will permit us to conclude, because we have this relation Z minus 1 is equal to the union of N0P, where P runs through the set of primes. So it's clear, because any integer can be written as NP, where P is where P is prime. So this relation is obvious. Now, if we suppose that P, the set of prime, is finite, this union, the union of finite closed sets, is a closed set, so this will be closed, and hence Z minus 1 is closed, so this set is open. And it's a contradiction, because we know that any non-empty open set is infinite, and we get the contradiction. So now we have so it's a beautiful proof, and I let you admire this proof. And now to support the channel, please like, subscribe, and share. And thank you.